When you connect an autonomous AI agent directly to external systems and APIs, you introduce a highly capable operator into your environment. But you also introduce an operator that can execute flawed logic at machine speed, leading to severe consequences if left unchecked. An agentic workflow exposes three primary attack surfaces. First, prompt injection, where malicious input overrides the agent's core instructions. Second, SSRF, or server-side request forgery. SSRF is an exploit where the agent is tricked into making unauthorized requests to internal, protected servers. Finally, there are executions that are technically authorized by the system, but logically malicious based on the user's actual intent. Standard statistical guardrails and basic system prompts fail here. A text generation filter cannot reliably prevent a determined model from hallucinating an API parameter that deletes a production database. High-stakes, irreversible operations require certainty, not statistical probability. Securing these workflows means discarding the idea of a single monolithic safety checkpoint. Instead, the architecture requires a multi-layered security pipeline. This pipeline operates across the entire development and deployment lifecycle. It begins with zero-cost automated static linting at the repository level and scales all the way up to mathematical zero-trust execution, verified in real time during runtime. Securing AI agency is an architectural challenge. It demands a dynamic defense-in-depth model where multiple independent layers of verification catch what the previous layers miss. The first line of defense sits at the very beginning of the CI/CD pipeline, designated as Tier 1. This is the pre-commit phase, acting before any code merges into the main branch. Static validation runs on every pull request at zero cost, instantly inspecting skill files to catch flaws, ensuring perfect formatting. Passing documents move to behavioral scanning. This scanner hunts hidden skill-ject scripts, malicious executables disguised as instructions, quarantining them before repository entry. By combining static formatting checks with active script scanning, these base layers form an automated shield. They neutralize basic structural errors and supply chain attacks at zero cost, long before the code reaches a live execution environment. Actions that modify skills or configurations trigger Tier 2 of the pipeline. This introduces LLM processing, carrying a low to medium compute cost, reserved for changes that affect how the agent interacts with external data. The third layer, adversarial testing via PromptFoo, bombards the agent with simulated attacks. It verifies resilience against SSRF, memory poisoning, and the exfiltration of PII, personally identifiable information, like social security numbers or private account details. Once the code survives the CI/CD pipeline, it deploys to the production environment, handled by a Model Context Protocol, or MCP, server. The MCP server enforces a strict zero-trust architecture. It uses Cerbos to apply attribute-based access control. Attribute-based access control is a system that evaluates specific properties of the user, the resource, and the environment in real time to determine permission, rather than relying on static roles. If the system evaluating these policies goes offline, the server executes a fail-closed circuit breaker pattern. It immediately blocks all high-stakes tool access, ensuring that a broken security subsystem results in complete lockdown, rather than default access. Tier 2 defenses guarantee that deployed agents can withstand active runtime manipulation, and that they only operate within explicitly defined dynamic access boundaries. Securing agents involves a strict economic reality. Applying intense, formal mathematical verification to every routine API call creates massive system bottlenecks and prohibitive compute costs. The Verification Depth Decision Framework Matrix maps action types to required security layers and costs. Low-stakes, read-only actions require structural validation. Moderate-risk actions escalate to adversarial testing. High-stakes actions, processing payments or system deletions, demand the highest scrutiny. For these specific operations, the system triggers Tier 3, deploying the Verify Safety tool and routing the request through the Formal Judge pipeline. The Formal Judge pipeline relies on the Z3 theorem prover. Z3 is a specialized computational solver developed by Microsoft that checks whether complex logical and mathematical formulas can be satisfied. Instead of guessing if a prompt is safe, Z3 evaluates the agent's execution plan and generates a definitive mathematical proof of safety. If the proof fails, the API call never happens. The depth framework targets computing power exactly where it is needed. It prevents bottlenecks on routine tasks while reserving intensive mathematical verification exclusively for irreversible operations. Pre-execution checks are powerful, but they have a limitation. They cannot stop an LLM's logic from drifting sideways during a long, multi-step execution loop. To secure the active inference phase, the pipeline deploys the Monitor-Safety tool, driven by SafeThink. SafeThink continuously analyzes the agent's chain of thought, the step-by-step reasoning process generated by the model. If it detects the logic drifting towards unsafe behavior, SafeThink provides real-time trajectory steering, redirecting the agent back to its approved operational parameters. Running parallel to this is the Record-Agent-Action tool, which feeds directly into an anomaly detector subsystem. The anomaly detector watches for critical runtime aberrations. If an agent gets stuck in a recursive tool call loop or attempts unauthorized secret exfiltration while executing, the detector catches and kills the process immediately. Every layer ultimately funnels into the Ironclaw orchestration engine. Ironclaw provides strict OS-level isolation, utilizing WASM sandboxing and Rust memory safety. WebAssembly forces code into a restricted environment, physically severing the agent's access to host machine resources. To ensure seamless integration, the pipeline includes a WASM tool sandbox in Python. This allows developers to mirror Ironclaw's strict environment and securely test tools before they are ever deployed. Integrating real-time inference steering with deterministic OS-level sandboxing solves the core unpredictability of AI. It ensures that even if an agent's logic fails, its execution remains entirely contained. True agent security is not a single gateway. It is a unified defense-in-depth architecture operating across three distinct temporal pillars. Pillar 1 handles pre-execution, securing the plan mathematically through formal Judge Z3 proofs before any code runs. Pillar 2 manages inference, dynamically steering the model's logic in real time using SafeThink to prevent cognitive drift. Pillar 3 locks down runtime, enforcing deterministic OS-level isolation through the Ironclaw WASM sandbox. When a high-stakes request enters the system, it must successfully navigate mathematical proof, cognitive steering, and physical isolation to complete its objective. Building safe AI workflows requires scaling verification to match the risk. It starts with zero-cost structural linting for basic tasks and ramps up to intensive formal mathematical proofs for critical operations. By implementing this multi-layered pipeline, engineering teams can deploy highly capable autonomous agents while maintaining the strict, verifiable security standards required for enterprise systems,